Hello everyone, welcome to another video tutorial of the FEM software. In this video, we will learn how we can link the MATLAB software to the FEM software. So, why we should link these two softwares with each other? Suppose we are going to solve this problem. We want to calculate the electromagnetic field generated by this coil inside this C core, iron core, and this iron bar. This is the structure of an actuator, and I want to calculate the electromagnetic force that is applied to this iron bar. So, as you know, the force is a function of the air gap thickness, right? So, you know that the main part of the electromagnetic energy is available in the air gap, and so when we change the value of air gap, the amount of applied force on this iron bar will change. So, as you know, if I solve this problem like what we did in the previous videos, we should create the geometry manually, and we should analyze and generate results. But this is a tedious work, because I should generate the geometry and do the settings manually for different air gap values. But we can do this by an external software like MATLAB. If I open the FEM software and open its help topics, here we have a section scripting, for example, magnetic preprocessor scripting. You can see these functions that we can use these functions to generate the model, define boundary conditions, materials, and solve the problem using scripting, not doing this manually. So let's also open the installation directory of the software. I installed the software in C FEMM 42. So here you can see this folder, that is M files of this software, the M files that we can use to generate the model. So this is, for example, for an electrostatic input, electrostatic output, or as you can see here, this is a magnetic input, magnetic output. We have different functions. So the first step for using of these functions is opening the software using the MATLAB, and then using these functions to generate the model. Let me show you an example. Here in MATLAB, I generate a new script, and let me save it to this folder. The name is test1. So I write CLC clear command window, clear the previous variables, and close all available figures, open figures, right? Just these three general comments of the MATLAB. So the first thing that we should do is adding this function to the MATLAB path. Actually, I want to use these functions. So I copy this path and I write here add path, this function. Right. So I can use functions, M files available in this folder. Right. So the first function that we need to use is opening this software, the FEM software. Let me close this open application. And after adding M files, if I write open FEM and I run, as you can see here, by running all this code, we can open the FEM software, right? So this is the procedure. You can study these functions here and their inputs to generate the model. For example, if I want to add some nodes, as you can see here, I can use this function, mi underscore add node x and y, x and y coordinate of the node. So I can write here mi add node, for example, 0 and 0. 1 and 0, 1 and 1, 0 and 1. So if I run this M file, right, we have an error here. The error is because I didn't generate any model. So the first thing after opening the software is generating a document. Actually, we have this function here, a new document, right? Creates a new document. So we should specify the doc type, 0 for magnetics problem, 1 for electrostatic, 2 for heat flow, 3 for current flow. So I need to generate a magnetics problem. So I write new document and the type is 0. Now if I run the M file, as you can see here, I generated this model and I created these 4 nodes. So as you can see, the model generation is much more flexible, right? We don't need to generate this model manually. So I can define geometrical parameters here in this M file and use them. For example, for this problem, we should solve the problem for this cross section. As you know, for this cross section, we are going to solve the problem. So I define these geometrical variables. These geometrical variables, this is x and y coordinate. I'm going to consider this as width of the yoke. I'm going to consider the same thickness for yoke and this iron bar. Also, this is my air gap. I write here G. This is I write width of window. Also, this is width of window, right? So using these geometrical parameters, we can define this geometry. So here in MATLAB, I write my variables, my geometrical parameters. I write here geometrical parameters. For example, width of yoke. Here the width of yoke, the yoke thickness is equal. The yoke thickness is equal 10. Excuse me, is equal 15. Width of the yoke. Width of the window is equal 50. The air gap is 3. Is 50. The air gap is 3 millimeters. So, how I can define the geometry? I can define coordinate of these nodes first. Coordinates of these nodes. And write a function to draw this geometry. So you know that we have 1, 2, 3, 4, 5, 6, 7, 8 points. Then we can define segments also after defining of these nodes. So here I write a variable, a dummy variable, P, or coordinates. You know that I can define 0 and 0. That is the coordinate of this point. This is width of window plus width of yoke. Width of window plus width of yoke and 0. This is width of yoke, the coordinate of this point. Width of window plus width of yoke and width of yoke. So the next point is width of yoke. Width of yoke, the coordinate of this point. The coordinate of this point is width of yoke plus width of yoke and width of window. The next point is this one, right? That is width of window plus width of yoke and width of window plus width of yoke. The next point is we should add up the y coordinate with width of yoke. So this is 2 times width of yoke, and this is the final point. This one. So we have these coordinates for this object, this C core. So here I can write this for loop. For example, I write for I equal 1, to size of p and 1. And I can use a for loop. So if I place a breakpoint here and close, if I run this, so we paused here in this line of the code, and you can see we have generated the model, but we didn't define any node. So if I print p, you can see the coordinates, and if I write here size p and 1, I want to get the number of rows of this matrix, that is 8. If I write size p and 2, I get the number of columns. So anyway, for I equal 1 to number of points, define we know that the x coordinate is pi and 1, and the y coordinate is pi and 2. So if I run, as you can see here, I defined the coordinate. I defined these nodes, right? So now I can change the geometrical variables, the value of geometrical variables here, for example 16, and regenerate the model. So using scripting, we can analyze different models in an easier way, right? So how we can define segments? If you see this function add segment, we need to specify the coordinate of x1, y1, x2, and y2. So after definition of nodes, I can define another for loop, right? For I equal 1 to the same segment size, and right here me add segment from p I1 to this one, I plus 1, I plus 1. But consider that we have an error here for the last point, right? When we reach at this number, the size of the number of points, we will get an error here because this index will be higher than the matrix length. So I write here size p and 1 minus 1. But if I run this code, as you can see here, we can generate this model, and we have an open polygon, not a closed polygon. So let's define a function here. Let's define a function here at the end of this M file. I write the name of this function as draw closed polygon. The input is p, coordinates, and so I cut these two for loops, paste them here. Here I define nodes and I define segments. Finally, as you know, because this is a closed polygon, I should write something like this from I to 1. Yeah, here minus 1. Finally, I write I equal I plus 1. Or this is better if I write here, draw a segment between the last node and the first node. So I can use this function here in my code, and even I can write a comment here, draw C code. So now if I run this M file, as you can see here, we have drawn this C core object. Now I'm going to draw the iron bar, this part of the structure. So you know that we should define this poly line. So here again, I define, I copy this, paste here. The first coordinate is width of window plus width of hook plus gap. So let me delete this, plus gap. This is 0. The coordinate of second point is 2 times width of hook. We have this, and finally this one. So here I write a comment, draw iron bar, copy this function, paste it here. So we define the function, and we can use this function in our code as many times as we need. So if I run, you can see here we generated this model. So now let's check. If I write air gap equal to 20 and run, you can see we can generate this model. In this case, the air gap is equal 20 mm, right? So now we should define coils. I define these variables. I define this variable. Let me zoom this variable as right, this variable as width of the coil, and this as height of the coil, right? So in this case, we have a variable here. I name this variable as vertical clearance, and we have a horizontal clearance here, horizontal clearance, HCL, because we used height of the coil here, or VCL. So I define horizontal clearance equal to 1 mm, width of the coil equal to 10, height of the coil equal to 30. For example, I use the 40 here for height of the coil. I write here 40. So the vertical clearance is equal width of window minus height of the coil divided by 2. As you know, this is the vertical clearance. We have 2 vertical clearance. So what is the input arm? If I consider this as input current and this as output current, so input arm is, we need to define the coordinate of these 4 points. So here I should define these points. This is width of hook plus horizontal clearance and width of hook plus vertical clearance, the coordinate of this point. So for the next point, I should add the width of coil here. Then I should add height of the coil, this one. And finally, I have this. So I write a comment, draw input arm. Draw closed polygon. And let's try. Run the code. So as you can see here, we defined this object. And finally, the output arm, I can copy this. Output arm is the first coordinate is minus width of the coil, the coordinate of this point. The y coordinate is the same. This is minus horizontal clearance. Y coordinate is the same. Minus horizontal clearance. And this is this one. Draw output R. Right? So as you can see here, we generated the structure. So now we should define the enclosure. So here the maximum length of here we have the maximum horizontal length of the structure, and this is the maximum vertical length. So I write LH max, maximum horizontal length, and this is the LV max, maximum vertical length. So here I can calculate HL max is equal width of coil plus horizontal clearance plus gap plus 2 times width of hook plus width of window. You can justify this equation, geometric equation, and the vertical one, I write here LV. Excuse me, this is LH, horizontal length. Max is equal width of window plus 2 times width of hook. So as you can see, the LH max is greater than LV max. But if you define another geometry, this is not always true, right? So I define L max is as maximum of these two lengths. This one and this one. Maybe you want to define another geometry. So I am going to find the maximum horizontal or vertical length of the structure. So here I want to define draw enclosure I define this is I am going to define this enclosure something like this. So we should consider this distance, this length, and this one. So how much greater than how much this enclosure should be greater than the structure? So when the value of air gap is high, we have a high amount of leakage flux here. Excuse me, a high amount of fringing flux here. So if you want to be more precise, you should consider the enclosure large enough to include all of this fringing flux inside the enclosure. So if you consider a small enclosure, you may lose the exact answer. So if I want to consider the length, the width of this enclosure twice the maximum horizontal or vertical length of the structure, this will be equal this number L max divided by 2, right? So here I have L max minus L max divided by 2 minus width of the coil minus horizontal clearance. What is the y coordinate? Is L max divided by 2. So I copy this, paste this one. This is L max divided by 2. So what is this coordinate for this point is L max divided by 2 plus width of window plus gap plus 2 times width of the yoke. So this is L max divided by 2 plus this plus this. The x coordinate here is the same and the x coordinate here is the same. So let's try draw this polygon, and if I run the code, you can see the enclosure here. I consider it twice. If you want to consider a larger enclosure, you can change that number. So we have created the geometry. The next step is putting material labels, as you can see here, for these objects. So this is the function for putting of material labels. Here, if I show you in magnetic object labeling command, so this is a set block properties, and here this is the function add block label. So I copy this function. Here I write add material labels. So I should add a material label here. Inside of this C core, I write here as width of yoke divided by 2 plus width of yoke, and width of yoke plus width of window divided by 2. This is the material of C core. Copy. I write here width of window plus width of yoke plus gap plus width of yoke divided by 2. This is material label of the iron bar. So if I run this M file, you can see we have defined these two material labels. Perfect software for 2D analysis. So we can generate the model using the MATLAB code and analyze different structures. And as you know, for most of the problems, the magnetostatic analysis is enough. And using magnetostatic analysis, you can design the model. For example, permanent magnet motors. Also, if you want to be more precise, you can use 3D commercial software. So this is a good position to start for beginners. We should add the labels for the air enclosure and these two coils. So here I copy this and paste. I write the width of window divided by 2 plus width of yoke. Width of window plus divided by 2 plus width of yoke. And here I write width of yoke plus horizontal clearance plus width of coil divided by 2. And here, right, this is, I can write, right, this is good. Copy, paste, minus. Let's see. If I run the code, you can see we have defined material labels properly, right? So the next step is defining materials and setting the properties of these blocks, defining the boundary condition and solving the problem. So let's pause here. I think the time of this video is high, so let's pause here and continue in the next video. Thanks for watching.